Okay, so today we're going to start nuclear chemistry. Things that are radioactive are the things that we're going to be talking about. So first of all, we need to define radiation. So radiation is small particles or high energy that's due to the breakdown of unstable isotopes. So in general, there are isotopes, in other words, different numbers of neutrons that can spontaneously break down and emit radiation. So the term spontaneously just means that it will happen. It doesn't mean that it will happen like right now, instantly. It's not the same thing as instantly. It just means that it happens. And we'll even see how that does happen to be predictable as its timing, but not necessarily which atom is going to do that individually. So as an example, we talked about chlorine 35 and 37. Those are stable isotopes, but there's a teeny tiny amount of chlorine 36 that every once in a while is formed. That hardly exists because it just breaks down so quickly and it becomes radioactive. Now keep in mind that all isotopes have the same number of protons. So all chlorine still has the same number of protons. Sometimes we drop this bottom number down here and just refer to it as chlorine 35. So the 17 is assumed because that has the same number of protons, okay? There's several different types of radiation, so let's go over those types of radiation for sure. First of all, remember that your mass number is up top and the protons are down here. So to determine how many neutrons there are, it's this minus this, okay? Now radiation is what's coming out of or off of a particular atom. First of all, let's start with an alpha particle. An alpha particle, name this little that's the symbol for alpha, is actually an emission of a helium atom. So the nucleus decides that it wants to kick out a helium atom. That means that the mass is 4, there's 2 protons, there are 2 neutrons. There's no electrons here, so that's something to be aware of. The next highest energy would be that of a beta particle, or B. This guy has a 0 mass, so he's not actually going to change the mass of the entire system, but he does have a -1 charge. We put an E here because this is like an electron, okay? So this is a very high energy electron. It has a -1 charge and no mass. Where this electron comes from, a neutron is going to split into a proton and an electron. And only the electron is given off as radiation. So imagine, here's your neutron, it splits into 2 and one of them goes away. The other one's left behind, right? So that means that your proton value will change because you're adding a proton. I'll show you how to do that in just a minute, okay? Probably the most difficult one to understand is that of a positron. Okay, so the positron is something called antimatter. And you may have heard this like in a science fiction movie or something like that. But antimatter is literally as it sounds. It's the opposite of matter. If antimatter and matter come together, they collide to make nothing. It's kind of like +1 and -1 make 0. They make nothing, but they make a lot of energy that the whole thing just gives off a whole bunch of energy. So this is actually an electron with a +1 charge. Don't get confused. This is not something you'll see very often. It's not something that just comes raining down from the sky. It takes a ton of time and energy to get a positron, much less 100 of them or 1,000 of them. And they're very hard to isolate because anything they come in contact with, they react with, okay? So this is quite rare. It's not something that you should see very often, okay? Here, instead of a neutron splitting into 2, a proton splits into a neutron and a positron. So a proton that has a +1 charge. So imagine my pen is the +1 charge. the thing with no mass takes the positive charge and the neutron stays there, okay? And then this goes away. The neutron is going to stay in the atom. These will probably make more sense when we go through examples, okay? Finally, the highest energy is that of the gamma ray. And so the gamma ray basically just emits high energy particles that are the highest end of the electromagnetic spectrum, okay? You might also see protons and neutrons as part of these types of equations. When radiation hits the body, it's bad. It's not good for you. We do use it for scanning, which we'll talk about next time. But it's going to go towards the cells that are in rapid division the fastest, which is why we can use radiation for cancer treatment, because cancers are constantly dividing very quickly. The problem with that is that radiation can also cause cancer, okay? That can be the source of it. So your cure can kind of give you cancer, but usually it's curing, not giving you cancer. Okay, so we have to use proper shielding to protect ourselves from these particles. Alpha particles can be stopped pretty easily because they're just the same as helium. So clothing, we'll just go ahead and stop those. Beta particles require much heavier clothing, and gamma particles require concrete or lead to stop them. It's the same type of thing that the concept if you're having an x-ray, you put lead over your reproductive organs. But if you end up working in this field, please, please, please protect yourself. The closer you are to the wherever it is that's emitting the radiation, the more danger you're in. Usually you want to stay behind a concrete wall when scanning is taking place. If you're exposed to this daily, that can be a problem. So make sure that you use safety precautions and watch for your own health in that process. Okay, so let's talk about the different types of decay and talk about how we do these equations, okay? So I want to go back. Remember that an alpha particle is the decay of a helium atom, right? So here we go. This Pu 240 releases uranium-236 and a helium atom. So I want you to look through this with me real quick. This helium atom is an alpha decay. See how we have a mass of 4 and 2. That's exactly what we said before. Well, these types of equations have to be balanced. And this is an equation saying this is what we start with, this is what we end with, and this is, hey, in the process of the reaction that happens. This arrow in some ways is considered to be sort of like an equal sign in chemistry. And what we're saying is mass can neither be created or destroyed, so it has to be the same on both sides. So you see how this is 240 up here. If we add 236 and 4 over here, that equals 240. And the same at the bottom, we have 94 protons. Here we have 92 and 2. Therefore, this is balanced on the bottom, this is balanced on the top. That is now a balanced equation. Okay, so see how I added these here? Okay, good. So that's what alpha decay looks like. Next we're going to do beta decay. Now with beta decay, remember what we're doing is we're starting with a neutron. It's going to split into a proton and electron and let off the electron, okay? So here my C14, it lets off that electron. 14 plus 14 equals 0. That's fine. But in the process of this being minus 1, I've got to make this number be 7. 7 minus 1 equals 6. But when we change the number down here, which symbolizes protons, remember? That is what defines the element. So when I change the number of protons, I have to determine the element. So do this one last. Okay, if this changes, that tells you that you've got to do something. Now the reason why that changes, if you remember, a neutron split into an electron and a neutron. The electron goes bye-bye. The neutron's now a proton, so the mass doesn't change, but the proton number goes up 1. These balance because 7 minus 1 equals 6. Kind of cool the way it works, actually. Okay, next, positron. Again, antimatter. Here a proton splits into a neutron and a positron. So again, the number of protons is going to change just in the opposite direction. Okay, so we start with another carbon. This is different than the carbon up here because this was carbon 14. This is carbon 10, okay? The overall mass does not change because we end up with a positron over here, so that's plus 1. But I now have a number 5 as my atomic number, which changes your identity down to the B, okay, boron. And the reason why is because one proton changes into a neutron and a positron. So that means that I took this proton and it's going to be up here, and then your number of protons will change, okay? Last is the gamma decay equations. Now the cool thing about gamma decay, it's not really changing anything. What we sort of designate as the start, though, is you start with 99M. This M means that it's metastable. I like to think of this as you're starting off standing on your head. It's not the most stable version of you. And energy is probably released when you come down off of your head, right? So this is sort of the gamma ray that's coming out. And then you still stand up. You're still you, but you release some energy. And what's happening inside that atom is it's just rearranging so that it's more stable that way, okay? Okay. It depends where we get these things as to where they necessarily come from. Some of them are naturally occurring. Carbon 14 certainly naturally occurring. But sometimes we actually make these ourselves so that we can use them in medicine and various other things. So here's an example of aluminum-27 bombardment. Bombardment means that I'm adding it to the reactant so that I can get something that might be a different isotope or radioisotope. So what I'm actually doing is I'm shooting neutrons at this aluminum. You can do that. So as you would imagine, I can add these guys up top. 27 plus 1 is 28. 13 plus 0 is 13. So since this is still 13, you still stay there for aluminum. Okay. So basically, the top numbers have to equal the top numbers, the bottom numbers have to equal the bottom numbers, okay? Just as a side note, you can measure radiation in a various numbers of ways. We can use the Curie, the Becquerel. In medicine, we obviously use the RAD, or radiation absorbed dose, quite often, or even the REM, because this is the radiation equivalent in humans, and that has some factors in there regarding like what type of radiation it is and how damaging it is. Radiation sickness is something that's very, very serious and is hard to treat too. So definitely be careful with your radiation exposure. Thank you very much.